Good afternoon, dear students. Can you hear me? Good afternoon. Can you hear me? Okay. So, thank you for feedback. So today we will continue with software. You may remember in our last lesson before midterm, we started to discuss the software part, final part of the components of the mechatronic system, basic components of the mechatronic systems. And today we will continue and we will finish the part of the software, and we use our time to design a simple mechatronic system using the simulation software. Today we finished the lessons, and next week, 24th of April, you make presentation. We will start with the group 1 and group 2, let me say A, B, C, and we will continue our next lessons. We will be busy with the presentations and evaluation of the homeworks.
Hocam.
Yes, any question?
Hocam, presentation, will the presentations will be online or?
The presentation, homework presentation.
Yes, it will be online.
Yes.
Or in class.
I prefer to be face to face, but you know the decision of the university will be mixed. That means some of the students, if they want, they do online, and some of them, if they want, they can do face to face. And in this case, it is difficult to manage. And I would like to say, you have to decide. If you all decide for face to face, I will be at the school, at the university. But if you say no, or some of you not, so then we will use the online, the presentation. But online means each one of each group will participate to the presentation. That means the total presentation of a group will be shared by the group members, and each one has to make the presentations, and I have to see. That means they have to use camera. Without camera, I will not accept it. So they will make the presentation, so I will see that. So this is also important. I'd like to announce from here. It seems it will be it will be online, because it is free for the students. Some of you, I know, it's not in Istanbul maybe, because I got some email from the students. So then the logical way is to decide for the online, and the online means each one of the group member has to participate to the presentation. That means present some part, at least one part of the presentation of the total homework, and with camera. I will see that. If only voice and I don't see that, I will not evaluate. That means he will get 0. It is very clear. Okay?
Okay, hocam. Thank you.
Sam, who is at the university? Sorry, one month. Lessons. Hocam, I came to the Zahban. Can you hear me, Zahban?
Yes, hocam.
You are at the university?
Yes, I thought we would have the face-to-face lesson.
Yeah, we can do face-to-face, no problem. I last week at the university, but nobody was at the university, and then
Well,
I decided to make.
Last week we had exams.
Before last week, I mean.
Yeah, before last week I said that I would come after midterms, but it's okay, Hojam. If you want it online, then all your courses will be online.
Next week I will be at the university. If you want, I will be at the class. No problem for me.
It's
so I
no
can,
problem
I
for
can,
me
but,
also, Hojam.
yes, but I came to the class and nobody in class, and I go to the office and make the presentation from the office. So I don't know if 2 or 3 students in class. I'd like to make face-to-face. So at the same time, of course, at the same time, we will use the internet.
Yeah.
That means this is the decision of the university. The university says some students can follow the lessons online. So that means I have to do the lesson online, execute the lesson online, whether in class or outside of the class. So in any case, will be online. But if some of you come to the class, so I will be in the class, and we will talk face to face, and we will maybe discuss some parts if you have any question. But beginning of next week, so that means next week we start. You start to make presentation about the homework. So we will discuss the homeworks. So that means you will present, and if you want to present at the university, with pleasure I will come. Okay. So it is your decision, because your decision, because I'm not, let's say, authorized to decide, because university decide both of them is possible, face to face or online. So then some students say, no, we cannot come, and if not all the students, in case of the homework presentation not existing in the class, not come to the class, so it doesn't make any sense. So you have to decide. As a group, you can say as a group, mesela group A, for example, you can say as group A we will be in the class. Okay, I will come to the class, and group C cannot maybe come to the class. They make in their presentations via online, and we check in the class. All of them are possible, but each group has to decide in the class. All of the member of the all of the member of the group must be in the class, not some of them in the class, some of them not in the class. I will not accept that. Okay. So please send the email, and I will act according to your email. If they say, if I mentioned, I repeat it once more. If one of the groups say we are coming to the university and we will make our presentation at the university, so I will be there, no problem. But all group members, you have to discuss with you. I mean, under you have to agree, and you have to decide. All of the member of the groups has to come to the university, not some of them using internet, some of them face to face. This is not acceptable from my side. So I'm waiting for your email if you want to make the presentations face to face. That means at the university. I will come with pleasure, no problem. I like to hear you face to face.
Hocam, what about other courses from you?
Which one? The other courses, the same. I mean, I'm available. I can come to the university. If you want to come, I will be at the university. But if you don't come into the class, I go to the office and I make the presentation from the office, because I mean it doesn't mean anything to do the lessons without students at the class, in the class. So please inform me whether you come or not, okay, by email. So I will act accordingly. In any case, I can come to the university, no problem. I will come. Okay? So then let's continue. You remember we started with the software and part one, okay? So we discuss the software, part software, how can we write the software, what are the possibilities to write the software, and we know what means software. You may remember the general mechatronic system consists of 5 parts: actuators, sensors, networks, hardware, software, and finally we started to discuss the part of the software. So and in software we said there are some languages, so let me summarize shortly. So the statement list, some of the the programming way of the programming, as the statement list, ladder diagram, function chart, and matrix programming, or basic languages, and some other languages developed, and some companies as their own software programming language. We discussed actually 2 of them, statement list and ladder diagram, and we said the statement list consists mainly of statements consist of commands, and they mainly consist of 2 important parts. One of them is the conditioning part. The other one is the execution part. So conditional part and execution part we discussed, and the program consists of several. It has a certain structure. And in this structure, the very important is step structure. So the program has to be written in step by step, stepwise, step by step. And so, in each step, we have sentences, and sentences consist of 2 parts: conditional part and the execution part. So all of them we discussed actually. The example of the conditional part. This is the part where we defined our condition for any execution, and we use mainly the if commands, and if input 0.0 is and if
you share the screen.
You don't see the screen? Oh, sorry. Thank you for remembering. So sometimes I lose the connections. Okay. So let's use the ekran paylaşalım. So is it okay now? Okay, then let's continue. Thank you. Thank you for feedback. So, we said the state here. So the main languages: statement list, ladder diagram, function chart, and matrix programming, basic language, and so on. But we will use the statement as ladder diagram. That means we will discuss. And each program, actually, if we discuss if we shall discuss the statement list, concept of several steps, and each steps consists of sentences, and in each sentence we have conditional part and the execution part of the programming. So the conditional part, we said, we define the condition for the execution. That means it is the section of the sentence where the conditions are required before you can activate the execution part, because for the execution, we need the condition for which conditions we are going to start the execution part. And there is an example here for the conditional part, and it starts with if here in this sentence you see this is a sentence: if input 0.0, if not timer 1, we discussed in the hardware part timer 1, or in other sentence, if input 0.2 and input 1.1, that means there is a logic AND here connected to inputs, and could be OR. We also discussed in our last lessons. So after conditioning part, we have the execution part, and the execution part start with then set or then reset or then jump, for example. So this is the execution part, and it is the section of the sentence where the output is activated. So, and generally we said we have in a PLC, in case of PLC, we have in hardware, we have inputs and outputs, and between are the CPU units, central processing unit, and central processing unit also includes the software we write and install into the PLC, and we decide within the program. That means the sentence of the program and the content of the program is actually defined in this program. We defined the conditions and also the executions, and the program, the central processing unit check the inputs, signals, and by reading the software, decide or create a decision for the outputs and create the outputs and send to the field, to the machine. And this is the way how the software or say central processing unit is working. And here we have, for example, the conditioning part and the execution part, conditional and execution part. And here we have the step start reset. So, and we can here write some explanation for that. And condition is in this step, this is the sentence we call. So if input 0.0, this is the conditional sentence, conditional part, and this is the execution part, then set output 0.0. Huh? So the conditional part and the execution part. And another step, so again, the conditional part, if input 0.1, the execution part we say then reset output 0.0. So in that way. But later on, if you somehow involve software, you will see there are many companies producing the PLCs. That means the hardware, and even if we learn some commands here, you will see they have also some special commands, or they have can make some modification regarding the commands. So that means you have to read the handbook of this companies produce a PLC, or participate to a short course to learn about the special commands or special structure of this company regarding the software. So one of the big companies is this Siemens, and Siemens, you know, this worldwide very known, and they produce, Siemens produce different size PLC. That means regarding the input, output, and central processing capacity. And if you want to use the Siemens PLC, so I'd like to recommend that you participate to an internal course provided by Siemens. So you learn and you start then accordingly. But you will learn you will see you can learn very quick, because main functions we are discussing in this program. But if you want to become a software developer, it needs more work, huh? It really needs more work. Okay. Single sentence within a step. So the program will execute the first step, that means step start. If the conditions input 0.0 is true, then it will execute the execution part. Let's say they will say set 0.0 here, as you see here. Start, step start. If input 0.0 is okay, I mean this is true. So the conditional part, if it is true, then set output 0.0. And we already, using our simulation software, we learned that how can we turn on the light, turn off of a light. But it is not possible to use the statement list in our simulation software, because simulation software is mainly designed to use the logical function, and we use the logical functions. And one of them is the, you see here, the function chart. So the function, logical function, one of them is the languages. And therefore, this is, I mean, in simulation software, we use the logical function. So, if the conditions, okay, the second sentence, if the conditions input, okay, next step, stop here, the stop sentence, or step, I mean, stop step. So if input 0.1 is true, that means if it is okay, so then set or reset, sorry. Set means set, and reset means reset. I mean, that means turn on and turn off, like this. Huh? Set means turn on, reset means turn off, or make it true or false, and so on. Okay, another here program, you see this step starts. Again, if input 0.0, then set output 0.0, or another condition and execute, conditional execution part. If input 0.1 is then set output 0.0, or another conditional part. If input 0.2, that means if input 0.2 is true, that means the signal elements connected to the input 0.2 give signals. So then it turns to true and it's okay. So if it is okay, then according to software, then set output 0.2. Can be light, for example, connected to the output 0.2, and then the light can turn on if the program set the output 0.2. Or another step, stop, for example, this is the condition 1. If input 0.1, that means if input 0.1 turn on, or if it is true, coming as a signals into the signals, input signals block, then the CPU units reset the output 0.0, output reset output 0.1, reset output 0.2, and so on. Okay. So actually we discussed all of them, but if the conditional part of the second sentence is true, then it will execute the execution part and proceed to third sentence without any exceptions, no waiting at second sentence, because it means otherwise, or if it is not, like this. Let's see here. here, for example, if input 0.0 conditional part, if input 0.0 is true, then set the output 0.0. Otherwise, that means if it is not the case, that means if it is not input 0.0, otherwise then reset output 0.0. This is the otherwise, whether or. Okay, so step execution with otherwise. So this is the explanation for that. The program will execute the first step start. If the condition input 0.0 is true, then it will execute the execution parts. This is this set 0.0 and proceed to the next steps. And step stop, and this is the next step stop. That means otherwise, if it is not true, I mean, if input 0.0 is not true, then it will execute the reset, because this is the command otherwise. If it is not, so do the other one. So this is the reset. Resets output 0.0 and proceed to next step stop, and so on. So there are some other commands like if, then, and, or, set, reset. We learned, sorry, if command or terms, then, and, or, reset, set, reset, otherwise, jump to. That means from one sentence to that. You give the address, the number of the sentence, and the program jump to this number and then come back again after finishing this sentence or part of the program. NOP, that means no operation, and that's the end of the program. So, and then we discussed the ladder diagram. So ladder diagram, another language we use to write the program. And it has also two parts, conditional parts and the executional parts. But this is a different structure, like a diagram, current diagram, or any other chart. Mainly the electrical engineers use they use this type of programming language. The mechanical engineers use mainly the statement list, because they get used to write such a program. I guess it comes from the other program language they learn during the studying time. And this is one example for the ladder diagram. And we also discussed, and we said, here we have the conditional part, and here we have the execution part. And we have here action line. And in this line, if here is S1, this is a contact, normally open contact. That means if the contact gets closed, that means if there's a signal, gets closed, and then set Y1. If S1, then set Y1, means that this is the conditional part, and this is the execution part of the program. And you see here the conditional part and the execution part. So ladder programming, when using a ladder diagram for programming, remember that it is a scanning program. That means it doesn't work step by step, and the CPU actually scan all this in a certain speed, which is given by the producer of the PLCs. So LCPS says cycle time is of the PLC, let's say, is 100 millisecond or 10 millisecond, or I don't know. You have to check. the companies producing the PLC, and it is different from company to company. Of course, they are trying to compete each other, and each one is to sell their product, offer, let's say, the more possibilities, but also according to the application. I mean, not too high or not too low, because high performance means also high cost. Low performance, low cost. But what is the decision point? The decision point is actually what we are doing. What we expect. What is the application? What is the need of the applications? So when using a ladder diagram for programming, remember that it is a scanning program. This means that the program will read from one rank to another, regardless whether the conditions of the previous rank was fulfilled or not. So without considering, because the all sentence, all the parts without, let's say, any waiting, without waiting for any conditions, read all the parts. The condition, if in any part conditions okay, then executions part will also execute it. So you have here an example for ladder diagramming. So the ladder diagram, what's that? So, and this is first part, rank 1, rank 2, rank 3, and this is the condition part, if S1. S is a symbolic name. We already mentioned in our last lesson. S is symbolic name. Instead F, S1. S1 is connected to the, let's say, input 0.0. Huh? There's a cross-reference list or reference list. And in these references, all of them are defined. S1 means, or S1 is assigned to the input 0.0. So these parts, all input, S1, B2, B1, and the other parts here, the condition part, Y1, Y2, Y3, we use to indicate or to address the coils for the valve of the valves. If S1 is true, then set Y1. That means if B2 is true, that means existing the signals, then set Y2. If B1 is true, that means it's existing, then set Y3. Okay. So from the ladder diagram, if B2 is activated, Y will be set regardless whether S1 was previously activated or not, which we discussed already. And here the ladder diagram S1, if S1 is true, then set Y1. And here we have AND connection, logic AND connections. That means it is connected in serial here. If S1 and B1 is true, then set Y2. That means, and here we have AND and OR connections. Logic here, for example, this is a OR logic. If S1 or S2, then set Y1. That means, or here, this is a NOT. Here, this is a NOT. If not S1, then set Y2. That means This is not, it means a not. I mean, if it is not true. So here, an example timer. If S1 and B1, then set timer 1, 5 seconds, for example, timer. Or if S2 and B2, then set timer 1 to 5 seconds. So this is here and or. This is or. And here we have signals which is connected to both of them with and. That means if S1 and B1 or if S2 and B1 and so on. And this is the PLC. We said, okay, PLC is an electronic device and has to be connected to the power unit. Power unit means 24-volt direct current, and you see here the input part of the PLC, input address, and here we have the, let's use another color here, we have the output part of the PLC, shown with O here, the output, so, and we have to connect, of course, we have to connect the 24-volt here. So 24-volt, because it is a device, and here the 0. This is the 0. Now this here maybe. So this is 24-volt, and this is 0-volt. And we have to connect all the inputs here to the input side, input signals, and all the output signals to the output side. Okay, so let's make a short break. I'm 10 minutes. Time is it? Okay, let's say 5 to okay, 5 to 2. So we start, let's say 2 past 10. And we will work on an example. So let's start, huh? Now we will discuss, we will let's say define a let's say simple mechatronic system, and we will design a simple mechatronic system using our simulation software. Let's try to start this simulation software also. And our simulation software I will try to design a simple mechatronic system consists of two linear actuators. You remember our last lesson or previous lessons, we already used or make an example with one linear actuator, a simple linear actuator. I'm going to use two linear actuators. This is this we did already. You may remember, huh? This is a simple mechatronic system consists of one linear actuator like this here, and we set here. Let's start the simulation, and this is our power unit. As you remember, power unit. We use the pneumatic energy, and we use since we use the pneumatic linear actuator here, and we said at the beginning of our lessons. Can you see the screen? Okay, I guess you see that. I cannot see your response. I mean your response because I only hear your voice now. So, okay, this simple mechatronic system we created in our previous lessons is a one linear actuator, and linear actuator is a pneumatic linear actuator. That means we use pneumatic energy to do the work. Could be hydraulic, could be electric, electromechanic, and so on. We discussed already in part of actuators. So since we have a linear actuator, we are interested to check the position of the linear act. That means to control the position of linear actuator. Linear actuator, you know, execute the linear motion. And this is a pneumatic cylinder, double acting cylinder, and has two important positions. One of them is the initial position, the other one is the response, advanced position. And for each position, we use a sensor. For initial position, 1B1, and for the advanced position, 1B2. And to drive these linear actuators, we use a 5-2-way valve, and this 5-2-way valve has to be operated. And to operate this 5-2-way valve, we use two coils. I mean, that means the valve has two coils, two solenoids, Y1 and Y2, as you see here, Y1 and Y2. And we said those are the outputs. Y1 and Y2 are the outputs. And the input signals are signals coming from the sensors checking the position of the piston, 1B1 and 1B2, and so on. Huh? And you see the control circuit. on the left side. On the right side, we have the power unit, power circuit, pneumatic energy derived by the pneumatic energy, and on the left side we have control circuit, control unit, and the control unit, control circuit. We use the electrical energy for the control. And you see, this is our input part, input signals here, as start 1 and 1B1 and 1B2. We have three input signals, and here 2 output signals, Y1 and Y2, as you see also on the control system, Y1 and Y2. Those are the solenoids which operates the valve, 5-way valve, and the valve operates the linear actuator and so on. And here we have relay contacts, relays contact. And relays we already discussed, we learned. Relays contact, and relays contact we use to establish the logic functions, like here AND logic. And here there is no, the AND or, just the connection via normal open contact. And this contact belongs to the relays. Here you see K1 and K2 and K3. And relays, you may remember, we discussed what is relay and why we use the relays and so on. And if the relay K1 is activated and the contacts of the K1 change and normal open gets closed, normal close gets open, and the same for the K2 and K3. And here, if we push the S1, you see here S1 is the start signals. Before I push the S1, I have to turn on the pneumatic energy here. This is the turn on of the pneumatic energy. Now our system has pneumatic energy. Now I turn on the pneumatic energy. Now I I push the start button, and you see, and piston moves forward and automatically back. You see. And this is automatic, let's say the mode. That means the system is working automatically. So it doesn't stop by itself. So there is a stop button here we designed already. And if I push the stop button, you see there is circuit here currently supply the coil of the K1, and if I push the stop button, I interrupt the connections here, these connections, and then the linear actuator will stop at the end of the cycle, like this. So it stops, and I can again start, push the start button. So like this here. I push once more. Okay, then and I can stop again at the end of the cycle. So this control system designed using the relays and relay contacts. And we said it is also possible to by writing a software. Using a PLC. We didn't use here the PLC. We just use the relays, and we established the control circuit using the relay contacts like here. So let's see whether I have it somewhere. I remember we did it. Where is it? The pneumatic, is it that? Take open, no, and TPM. Pneumatic control circuit. Oh. Which one is this? No name project 4. No name project 4. Okay. Project 4, 5. Let's see the 5. What's the 5? Okay. So this one. Project 5 with PLC. Same project. That means same power unit. We use the PLC here. You may remember. And in this PLC, this is the input part here, and this is the output part. And all the inputs we connect to the input parts, and all the output signals we connect to the output part. And we have to also connect the PLC, our PLC, to the power unit, then to the current voltage, like 24 volt here, to the 24 volt here connected, and the 0 volt is also connected. You see our 24 volt direct and 0 volt. So if I simulation, share the simulation like this, you see we will have the energy here, 24 volt direct current, and pneumatic energy also available. And I have to turn on the pneumatic energy for the system, for our linear actuator like this here. So then I have in the system power unit pneumatic energy, and I have also electrical energy for the control system. So again, like our examples before, we realize using the relays and relay contacts. If I push the start button here, so the first input signals will arrive the PLC, so like this, and then it starts to work like this. And with that, we established here the 3 second and so on, the timer. We use the timer within the PLC. So piston arrive the initial position and wait 3 seconds and then come back automatically. That means we have an AND connection there. Connection means piston or the linear actuator first has to arrive the advanced position, and after checking it is arrived, the advanced position is arrived, then the piston has to wait 3 seconds after arriving the position, then should come automatically back to the initial position. So we use the first time the timer here, and you see in case of control, I mean control system, we already discussed in hardware, in part of the hardware, timer, counter, flux, and so on. We use here the timer to, let's say, to stop the cylinder for a certain time in any position we want, and then after time passed, then piston starts again to move. So, and also we said that the control can be, within the control we can, I mean, check the position, we can check the time if it is needed, if it is necessary, if it is needed for the solution. We can decide according to the time, we can decide according to the position, we can check also the pressure or if, in a certain position, and we can decide according to the pressure or any other, maybe level and so on, any other physical quantity. we can decide, or we can use some of them. And here, for example, like we use the position and the timer. We said if the piston arrives the advanced position, he has to wait 3 seconds and then has to come back. So all these possibilities or all these control requirements we can consider, we can use in the control system. So the function of these simple mechatronic systems, I am saying simple because there is one linear actuator, only one linear actuator. Huh? So only one linear actuator. And I will show you another mechatronic system. And this mechatronic system consists of 3 actuators, 2 linear actuators and 1 rotary actuators. So you can expand. I mean, you can actuators, rotary actuators, linear actuators, could be pneumatic, could be electromechanic. I mean, you can use the electric motor and so on. Yeah. So all of are possible. You can design the control system for a simple mechatronic system, or you can design a mechatronic system. And I expect later, I mean, if you want to come to the final, if you come to the final semester, I mean, if you come to the position where you have to make the graduation project. So I hope you select some graduation project regarding the automation, industrial automation, to design a certain function unit or a certain part of the machine or a simple machine, and using hydraulic or pneumatic, sensoric actuator, all these 5 components of the mechatronic system, a simple mechatronic system, industrial automation. And today's industrial automation is very important in our industry. All the production lines, all assembly lines are getting automated. Because we have to produce fast, we have to produce safely. I mean, the human involved in the production process or assembly process to keep the conditions constant is not always simple or always, I mean, beneficial. Therefore, we use the automated system today in the industry. We have to produce more, we have to produce precise, we have to produce at any time same quality and so on. So industrial automation is very important. And industrial automations means mainly consists of actuators, sensors, network, hardware, and software. Whatever you are going to design, I mean, as a machine or as a function unit used in the machine. Okay. So in this example, we have 3 input signals, as you see here. 3 input signals, start, 1B1 and 1B2. 1B1 and 1B2 are checking the position of the linear actuator, and start is already to start and I mean to stop. We use if we push 1 time first and it starts, and the second time we push second time it stops, like this here at the end of the cycle. And in the PLC we use here, we write a program. I mean, according to this program it works. According to the program it works. What means it works? The program is executed by the CPU, checking input signals and checking also what is written in the program, sentence by sentence. And according to the inputs and the program, the CPU create the output signals and set the output signals, and output signals in this example goes to the Y1 and Y2, and those are the solenoids belongs to the 5 two-way valves, 5 two-way valves, and the 5 two-way valves operates the linear actuators. Do you have any question regarding this simple mechatronic system? No, okay. If not, then I will. So I'm sorry. I will select another one. Pneumatic control manufacturing. And okay, this one. So here we have, you see, it is quite. I mean, we have the problem regarding the view. Where's the view? Okay, here. Maybe to make it. How can we start size view details? Okay. So maybe you see more. You cannot see everything, but you see more regarding the circuit diagram here. You see, this is the circuit diagram. The pneumatic, again, we use the pneumatic energy, pneumatic system. We have here two linear actuator. This is the one here, one of these linear actuator. This is the second linear actuator, and this is the third linear actuator. This is a rotary actuator, turning left and right. This is linear actuator, single acting linear actuator, and this is double acting linear actuator. What is the function of these systems? Let's imagine that we have a workstation, and this workstation operator put the material per hand into the working station, and the working station has a rotary actuator to turn the materials, the workpiece, 180 degrees left and right. And the left and right, the position will be checked also the sensors 1B1 and 1B2. And if we put the material into the workstation, this linear actuator has to fix the material in this position. That means the material during the operation shouldn't move in any directions. So that we have here the drilling unit, and the drilling unit, this is the linear actuator, come down and make a hole in the or cut a screw in a hole which is located in the workpiece somewhere, of course in the position. And then after finishing this process, that means the cutting the thread, so then the piston, the cutting tools go back into the initial position, and then the fixing is linear actuator gets back, and then the workpiece is free now, and the rotary actuator change the position turn the workpiece 180 degrees left or right. It's not important, left or right, and bring it into the other position. So in the other position there is another hole, and this hole will be also, in this hole will be cut this thread again with this linear actuator, and we write a program here and install into the PLC GraphSet PLC here, because it works according to the program of GraphSet. GraphSet is also used programming language by certain companies produce the PLCs, And you see here the input signals, all the input signals. Here the start signals, we have here the 1B1, 1B2. This is for the cylinder 1 here. Where is that? This is the actuator 1, 1B1 and 1B2. And then 2B1 and 2B2. This is the actuator 2, which is the actuator 2. This is actuator 2 here, and you see 2B1 and 2B2. Those are the sensors checking the position of these linear actuator 2. Because we have to label all the actuators, all the sensors, all the components actually involved in the control system. And so we have to label it. We have to define, give a name and label it, because in case of trouble, we have to make the troubleshooting. I mean, to solve the problem. So then we need the circuit diagram. We check the circuit diagram. What is how is the function of the machine? And in circuit diagram, we see some labels, and all these labels must be also seeable on the machine. So therefore, we use the same label for the circuit diagram, for the components in circuit diagram, and also the same for the same components in the machine. This is the machine side. This is the circuit diagram, and same for inputs, all the inputs, and same for all the outputs. So let's see how does it work. Let's choose the simulation. Okay, simulation starts. You see the PLC part and the inputs here. We have here 1, 2, 3, 4, 5, 6, 7 inputs. 7 inputs. One we use for the start. The other 6 are responsible for the 2 linear actuators, 1 rotary actuators. That means we use 2 inputs for each actuators to check the positions of the actuator, because each actuator has 2 positions, initial position and advanced position. And we connect all these input signals to the input part of the PLCs. And this is you see the input part here. And some inputs are active. You see now, for example, the inputs 1 and inputs 3 and inputs 5 are already active. And let's see why are they active. But the start is not active because start button is not pushed. So 1B1 is active. Why 1B1? Let's see where's the 1B1. 1B1 is the sensor, position sensor for the rotary actuator here, and checking this position. I mean left position. And 1B2 check the right position. So we see here, because of the point is indicated, that the rotary actuator take this position, the left position, and therefore, since it is in this position, 1B1 is active. Therefore, we get the signals. That means PLC get the signals from 1B1. And what is 1B2? 1B2 is not active. And you see, both of them cannot be active at the same time on the other side. And the other one, 2B1 is also active. And let's see the 2B1. Where is 2B1? This is the actuator number 2. So 2B1 is the initial position of the actuator 2. And okay, and we see that the actuator is the initial position. Therefore, 2B1 is active. And you see the input 3 is active because of that reason. And here we have another active sensors. This is 3B1, and 3B1 belongs to the actuator 3. And you see the actuator 3B1 is okay. You see here is also the 3B1 is checking the initial position of the actuator 3. And since this actuator is in initial position, so 3B1, 3B1 is also must be active, and therefore all these three inputs are active, and we see from the PLC side, from the side of the PLC, that inputs are active. But the outputs, none of them is active. I mean Y1, Y2, Y3, Y4, Y5. So all are the solenoids operating the actuators. Here, for example, the Y1, here Y1, Y2, and Y3, Y4, and Y5, as you see here, belong to certain or operating certain linear or rotary actuators. So let's see how does it work. And we have a program here inside of the PLC. And if you want to see that, the program inside is not, I mean, it's written here. The program you see, this is the program, the software part here. Step 1, step 2, or let's say it is the structure of the graph set way of programming with graphs in graph set. Is step 1, step 2, step 3, 4, 5, 6, 7, and then here we have M10. M10 means from here, if this condition, this is the conditional part here. This is the conditional part, this is the execution part. Conditional part, if this condition is fulfilled, then the program jump to the M10. Where is the M10? M10 is here. This is a sub-program here. You see, M10. And that means, and M10, we have here E10, that's input 10, and come to this step and continue from here. If it is finished, then come back to the stop the program 10 and come here, and from here go to the start position of the program and to the step 1. You see, if we have more actuators in our system, our control system getting a little bit complicated. That means we have to handle more input signals and output signals. And maybe we need to consider more condition, more complex conditions for the control system. But it is a system. It is a system. That means if we learn how can we realize a simple mechatronic system consists of only one linear or rotary actuators, or two linear or rotary actuators, or mixed. The complex system have also same structure. Therefore, they're not a big problem. And I'm sure you can learn and you can do it. So let's start the simulation. Okay, you see sensors are active, and I have to turn the also pneumatic energy turn on. And I turn on the pneumatic energy. You see the pneumatic energy is also turned on, activated, and active in the circuit. So if I push the start button, it starts to work like this. And you have to see what has happened in the system. So this is our rotary actuator, and there is a workpiece on this rotary actuator placed by an operator, and this rotary actuator turns left and right. If the rotary actuator arrives the position, the linear actuator, this single acting linear actuator, fix the workpiece, and during this fixing this time, the actuator 3 C3 come down and cut the screw or thread into the hole. And this is the actual function of this machine. And this is a real machine, and we did it. I mean, in a company, we realized this machine. This is working very properly, very nice. This is reality what I'm showing to you. And this is not an artificial developed example. It's a real example. You can also automate the supply of the workpiece. That means not by hand, by operator. Can let's say the workpiece can be supplied by robot or simple robots, so that the system can be fully automated. And you see here, the inputs are changing. That means the actuators are moving to initial position or to advanced position, and it has a certain, I mean, the motion sequence. In a certain sequence, the motions are occurring. So, and this sequence is very important for the process. And we create this sequence using the control system, our control system. That means our control system, PLC, check the inputs and read the program written in like this here. You see the program here. And you see the sequence of the program. Step 1, we'll start step 2 and then step 3. You see green. If the step is active, it gets green like here. You see here, and then here, and so on. Huh? You see the program here, program steps. And here you see the, I mean the motion of the linear actuators are also shown here. We have, sorry, one of them is a rotary actuator. We have here this is the rotary actuator. Those are the linear actuators. Huh? So the rotary actuator takes this position and linear actuator fixed, and the other one is the come down and make it cut the thread and go back, and it repeats. You see, it repeats again. Huh? And with this simulation software, we are able to check or to see, to make it seeable, all the motion sequence and all those things. And as I mentioned, the first one is the rotary actuator. Take this position and go this position and stay this position for a certain time. So you see, this is one position, left, let's say this is the right position, come to the right position, wait there, and then if it is finished, come there. And in the position, the fixing cylinder fixed, and the drilling, make this drilling, and then it repeats again. Huh? Come back, and then it repeats again. Okay, so let's stop it at the end of the cycle. Okay, so this is the end of the cycle, and we stop it. Do you have any question? Is it interesting for you, the simple mechatronic system like this? Maybe you don't listen, huh? Okay. Let's make a break, and we will meet again 10 past 3. So let's start on. Okay. In these lessons, we will work on an example we will create from the zero together. A simple mechatronic system consists of two linear actuators. And our scenario is we have, let's say, one pneumatic cylinder, linear actuator, and for the fixing the material, let's say, we could have, how can I show? So this is, let's say, this is our workpiece. Let's have a workpiece for okay, here. So we have an. Can you see the screen? Yes. Okay. Thank you, Mohammed. Thank you. Thank you, Görkem. Okay. So let's say we have such a workpiece, and we can say, okay, this is our workpiece, and so establish it. I'm trying to draw the sketch, what we are going to do. Use another color, okay, like this here. Okay, this is the workpiece here somewhere. Okay. And this is another one. Okay, let's. Okay, let's. Okay. Okay. So this is our workpiece, and we want to fix this workpiece somewhere in this position. The linear actuator we are going to use, and I can use this one, for example. Okay. So this is our linear actuator. One of them is the cylinder we fixed here. Okay. Let's choose another color here. Maybe this one, and So this is our linear actuator and has to be fixed somewhere here. So how can I show that? A linear actuator here. Use color, okay. Okay, so how can I fix it? I need for this type of component, maybe. Okay. Um, uh, okay, let's assume that we can fix it somehow. So, and this is, okay, our linear actuator views also in vertical direction, like this, huh? And we want to add the drilling component here somewhere, huh? Send it back, okay. Like this, okay. So we want to make a hole here on this surface in a certain, let's say, the dimension. So first of all, this cylinder, let's say this is cylinder A or cylinder 1. Let's use the label. This is the linear actuator. Linear actuator 01. And use the black one here. Okay. This is the linear actuator 1, and we have another one, linear actuator 2. This is the linear actuator 2. Okay. First, the linear actuator 1 moves and fix the workpiece in this position. So in this position. And then if it is fixed, then the the linear actuator 2 moves downwards and making a hole here, like I can show you that. or check the hole maybe. Could be also quality control, check the hole inside. Let's bring here. Like this. And maybe I can use another color here like this. Okay, so it's checking. We are going to check this hole here, huh? Is it existing or not? The quality control station. This is the scenario, but in the reality we have two linear actuator. One of them is the fixing or the keeping in the position of this workpiece. This workpiece is kept in this position, and then the control cylinder come down and check whether there is a hole with diameter, with this diameter. This is the critical diameter. Let's say here we have this diameter is very critical here with this diameter checking. Let's use the color red since it is important diameter. Like here we see that. Okay, here. Okay, we are checking this diameter. Let's use another one. Okay, and turn it 100 degrees. So, okay, here like this. Huh? We are checking this diameter is okay or not. So, in a summary, so we have two linear actuators, and with these two linear actuators, we are one of them. This linear actuator is 1, 0 is fixing the workpiece in this position, and the second one moves downwards and check the hole. Is it correct or not? So on. So that means we have two linear actuators. We have to coordinate the motion of two linear actuators. So now we are going to define the sequence of the motion, sequence. So then it means, first of all, the so can we define the sequence of the motion? Let's do it in that way. This is our sketch, and the motion sequence must be like this. Let's say we have here the lines. Okay, copy. And then second one here, this is the actuator 2. And again, copy that, actuator. Okay, and another one here. Okay, then use this one here, this line. Okay, then this is here, copy and bring here. That means this is the shows the linear actuator 1, and this is the linear actuator 2. Let's bring here. Now we are going to define the motion sequence. So I'm going to use another color for the line. So then use the, okay, so let's take this one. At the beginning, all the actuators are in the initial position, and I will use here the color. I will indicate so that way the line, and use the color here, the blue, and then and the other one is also in initial position. It is in initial position. Sorry for that. So it is in initial position, 0 position, and let's copy and use it for also for this actuator. It's also in, and this is, let's use the red one. Okay, and this is the position 0, and maybe I will take it a little bit down here. Okay, and this is, I have to reduce a little bit. 18 is okay. So, and this is the position. Okay, so for the actuator 1. Okay. So, and this is position 0 here. 0. 0. Position 0. And position 1 here. 1. And let's reduce it to the 14. Okay. So, initial position, advanced position. 0 indicates the initial position, 1 indicates the advanced position. Let's take it a little bit in this direction here. So, okay. Then I will use also that for the second, for the first actuator here. Initial position, advanced position. Okay. So, okay, this is the actuator 1 here. You see the actuator 1 already defined. This is actuator 2, and initial position is 0, advanced position is 1. So let's define this motion sequence. If the workpiece is in the position, then the linear actuator 1 has to move and fix it in this position. So this is the scenario. So has to move means we have here 4 steps. 1, let's say this one, and let's define the, okay, okay, 2, 3, and 4. So first, the first one, and the actuator 1 moves. First step moves here, and I have to use also the same color and make it a little bit understandable. So, and during this time, the first one is the second actuator doesn't move. Huh? So then, if the first actuator arrives initial position, then the second the piston moves in that direction, and that means in advanced position, comes into the advanced position. Let's use the same. Okay, and then during this time period, the first one is keeping the position. That means doesn't move. So let's have here that it is must be also okay, this color. So then that means if the first actuator moves in the initial position and fix the workpiece in that station, then it is fixed, and then the second moves downwards and control the hole, and after control come back. That means move back into the initial position, and we can show that like this. Okay, come and okay, in this initial positions. Okay, and during this time period, and the first cylinder is keeping this position here. Huh? So initial position, because it's continuing to fix the workpiece in that position. And after checking is finished, then the that means the second actuator come down and check the hole, and they go back to the initial position like this, and then this piston 1 or the linear actuator ones come to the initial position. So, and let's also draw it with color, the same color, the blue. Okay, then during this time, the other actuator, that means actuator 2, doesn't move and stay in the position, keep its position. And let's also keep it like this. And so this is the motion diagram. Huh? This is the motion diagram, you see. Or the motion diagram show the motion sequence. The first actuator start to move and come to the, we can indicate this is the first step here. Let's use this here, copy. Okay, that's right here. This is the first step, and then in copy, and you see here this is the second one, is right here, the second. Okay, then the another one, the third step, this is the third one, and here used another one is the this must be 3 actually. Okay, 3, this is 4. I will explain why. This is 2, and this is 1. This is 1, and this is 0 here. 0. Okay. And okay, this is 1 here. 0 step 0, 1, 2, 3, and here we will have the 5, 4. 4 we write here. The 4 here. Where is it? So this is 4. Okay. So in first step, the linear actuator moves from the position 0 to the position 1. And during this time period, the linear actuator 2 keep its position, doesn't move in the initial position, stay in the initial position. After the cylinder 1 arrive its initial position, so then this linear actuator 2 starts to move, check the hole, and starts to move, check the hole, and come back. And after coming back of the linear actuator 2, then linear actuator 1 moves to the initial position, and we come to the initial to the position where we did start, like this here. Huh? So this is the position, final position. Then it repeats again. This is the one cycle. From this is the first step, second step, third and fourth step, and it starts from 0. And here this is the one cycle time. Here this is the, we can say this is the one cycle time. Let's show it like this. Okay, one cycle time. So in between, 1 cycle time. So like this is the 1 cycle time. Okay, here. Okay, so how can we realize that? I mean, how can we organize the motion sequence like this? So to organize the motion sequence like this, we have to use the sensors, isn't it? 2 sensors for the actuator. 2 sensors for the actuator to check the position. So then, okay, we can use 2 sensors to, let's say, the 2, and let's use 2 sensors here. And this is, let's say, 1B1, 1B1 must be okay, and the let's reduce that 14. Okay, so let's say this is the sensor 1 for the cylinder 1. We are checking this position, and let's use the just different color like this one. This should be sensors, and let's copy that and replace. So this is the then initial position 1B. So 1B1, 1B2. Sorry, this must be 1B. No, this was correct. 1B1, 1B2, the advanced position. And we have to use also 2 sensors, 2 different sensors for the linear actuator 2, like this here. And let's say this is 2. Since it is 2, we have to write it 2, actuator 2. And here we have to use also 2, actuator 2. 2B1 and 2B2. So 2 sensors, huh? So like this. Okay. Let's make it a little bit understandable, huh? Okay. So we already defined this sequence of the motion. That means the first linear actuator moves forwards to the initial position, to the advanced position. Then the second actuator starts to move into the advanced position, and after arriving the advanced position, checking the hole, come back to the initial position. Then the actuator, linear actuator 1, come back and lose the fixing. I mean, to lose the workpiece. So we are going to realize these motion sequence. So this is our aim. So for that, let's keep it as it is. We will come back again and see that. Come to the simulation software, and let's we have to have a new file. And now let's have 2 actuator here, linear actuator. Rotation, how can I do that? Okay. Like this. And the other one is, it will fix the material. Or let's fix it from that side. also could be. And this we have to use, let's say, turn 90 degrees. Then 100 degree again. Rotate 100 degrees. So, like this, huh? Those are the position. Here we have our workpiece somewhere. And let's bring that here. Okay. And draw that somewhere here. And let's define the sensors for that. This is our linear actuator 1. Properties. Okay, and actuating labels. This is 1B1, 1B1, and the start position is 0, and the end position is 100. Oh, sorry, 0 also. The start position is checking here. Then we have 1B2, and we have, since stroke is 100, let's define as 100. Okay, good. Then we have to give the name 1.0. This is our actuator, linear actuator 1.0. Okay, then. So this is our linear actuator. You see here, linear actuator 1.0, and this is the 1B1 and 1B2. And same for this one, huh? And again, and this times we have here 2B1. Oh, this is second actuator. 0, 0 is initial position. And 2B2, this advanced position is stroke 100. And also here, right, 100. And this is our actuator, linear actuator 2.0, second linear actuator. So this is also already defined here, huh? Second actuator. And you can see also this is the first one. Okay, you can label it somewhere. To derive these two linear actuators, we need valves, as you remember. This is 5 two solenoid, 5 two-way valves. So then let's configure these valves. This valve configuration has from two sides electrically actuated. Okay, so I think it is okay now. So, and we need two of them, but first we defined also the exhaust port. Okay, and here we have also the exhaust port. Okay, this small one, good. So, and we need two of these valves for each linear actuator, as copy and paste. So we need one for this, and this one is for that cylinder. Okay, we can maybe do it like this. So, and let's connect here, and this one to here, and also this connect here, and this one is also here. So we establish the connections. Okay. So then we have to define the coils, huh? So since this is our first actuator, let's take this label here somewhere. Okay, and this label we can take here somewhere. Similarly. So this is coil 1. Or let's start here from this coil 1, Y1, Y1, okay. This is Y2. We are labeling, defining coils or the solenoids like this. Oh, this is not correct. It must be Y2. Okay, Y1, Y1, and Y2. Okay, Y1 and Y2. Correct. So then here Y3. Okay, Y3. And here we have Y4. Y4. Okay. So now we finished okay, the power unit. Power unit we finished. Actually, we have, okay, we not finished. We have to add also the pneumatic source of the pneumatic energy, and we have to use the service unit here, and the service unit we have to connect, and we have to use a pneumatic switch turn and turn off the energy like this here. So can use that here. Okay. Here. So then our circuit is now completed. Power circuit is completed already. So but the power is getting lower, so I have to connect to the power of this. So then move this to the place where we have the power. Okay. So let's add the power. There is that here. Okay. So, so the power circuit is okay. So that means we can check the power units, but it is normal. Okay, it can move. Now we have to also, okay, all the sensors are there. So, okay, so then we have to use a PLC programming to write a program that function there. No, not a logic unit like this here. And we need the 24 volts somewhere. Our 24 volt, where is it? Here. This is 24 volt. Okay. So 1 second. So 24 volt. Okay. 24 volt. Okay. So then, okay, 24 volt. Then we need the 0 volt. Take the 0 volt somewhere. Where is it? 0 volt here. Okay, and let's connect the PLC to the power. It's also finished. So what we need, actually we need following. We need the input and output signals. So the input signals, where is the input signals? We need a start signal somewhere. This is our start signals here. Let's say this is our start signals and has to be connected to the voltage here. Let's take it a little bit so in that directions. And this is the input. Let's say we use the first input for the start signal. Let's indicate it with start like ST start signals. ST it's a symbolic name. Okay, and then B1, B2, B3, and all those signals. But I'm going to use a simple sensors because I don't have enough place here, space. Okay, so then, okay, let's use that. Here, let's indicate magnetic limit switch or read contact. Okay, could be read contact, and the name label it 1B1 like this. It's also connected to the 24 volt, and this is our input 2. Okay, and let's copy it. It's not indicated 1B1. Why not? Properties, display it. Okay, so link display. Border display. Okay, so 1B1 is already here shown, and we can move a little bit to the side, and let's copy that. Copy, where is it? Copy and paste here. And this is 1B2. Must be 1B2. We have to change the name 1B2. Here, 1B2. Okay, and connect again here. And this is our input. 1, 2, 3. Okay. Let's move it a little bit to this side. Okay, and so and in total we can move this also a little bit. Okay, because I need place for the other sensors. Okay, here let's copy that and also copy and paste here the other sensor. This is the 2B1. Let's write 2B1. Okay, this is 2B1. Okay, and then the next one, let's once more paste here, and this is will be okay 2B2. Let's properties right here. Okay, 2B2. Okay, this is also finished. Now let's connect to the 24 volt like this here. All the inputs, and this we have to bring here down a little bit, huh? And then here input signals. Okay, and this is another input signals. You see, all the inputs are connected now, huh? So we connected all the inputs. We have 5 input signals. Start 1B1, what's that? This is somehow a problem. 1B1, where is it? Where is it here? 1B1, okay, 1B1, come on. 1B1, okay. So this is 1B2. This is 2B1. Let's, okay, 2B1, this is 2B2. Okay, so now let's the outputs. We have to connect also the outputs. Where is the output? Outputs are the the solenoids. We have to select the solenoid somewhere. Find the solenoids. Where are the solenoids? Solenoids control central, manual operation, and actuators. So no, where is it? Here. Here must be solenoid. Okay. No, this one. Okay. So we have two solenoid 1 and solenoid 2. 4 we need. 3 and 4. So, and let's define it. Solenoid 1. The name must be given here, Y1. Y1. This is Y1. Okay. And this is Y2. Okay, this is Y2. Y2, this is also okay. So, and here, this is Y3. That's right. Y3. Okay, Y3. Good. Okay, this Y4. Y4. Okay, here. That's Y4. Okay. So all solenoids are, the outputs are also defined. Now we have to connect them. Not that. So this is let's here. This is must be to the ground. 0 volt connected and 0. Okay, and this is also 0. So the Y1 must be output 1. Output 1. Okay, and this Y2 output 2. Okay, output 2 and output 3 here. Okay, and output 4. So all the outputs are also connected like this. So you see, we establish the hardware, and we establish the circuit, and we connect all the signals, input and output. Now our problem is to write the software now. How can you write the software? I mean, we said first of all, the linear actuator 1 has to move to initial position, fix the part, workpiece, and then the linear actuator 2 moves down and control the hole and come back, and then the linear actuator 1 come back to the initial position. This is the sequence, motion sequence. So let's assume that if we push the start button and the linear actuator 1 is initial position, that means the B1 is in its position, then Y1, the Y1 gets the signals. If Y1 gets the signals, what will happen? So then the piston moves forward. And then secondly, if the 1B2 arrived, is active, that means the linear actuator 1 arrived its final position, then we have to activate the output Y3. Then if it is Y3 active, then the linear actuator 2 moves in advanced position, and in advanced position, that means 2B2 will be active, and then since 2B2 will be active, then 2B2 will activate the output Y4 and then come back, and then 2B2, then if 2B2 is active, then it will activate the Y2, and the piston, linear actuator 2 will come to the initial position. 1 come to the initial position. So that's what we want. We have to explain to the PLC. That means we explain. We have to write a software for that. So for software, we will let's make a 15 minutes break, and after 15 minutes we meet again. Okay? So we write the software. Okay. Dear students, can you hear me? Okay, thank you. So I would like to suggest to continue next lesson next week, because so I have to some unexpected urgent problem I have. So please, we'll complete this part of software next week. At the beginning, we need 15 minutes maximum. Then we will start with the presentation. Okay. That means you will start to present your homeworks. Okay, have a nice week. Bye-bye.